Hello, everybody, and welcome to our third TechLabs Talks about neuroscience and technology solutions together with Surjo and Jonathan. And before we start our talk, I just want to introduce myself really quickly. My name is Marcia Maxwell, and I've been with TechLabs for about a few months now. And currently, I'm supporting the new strategy team here at TechLabs. And today I get to guide you through this talk. I'm very happy to be moderating today because I'm actually a neuroscientist, and this is one of the topics that's really near and dear to my heart. So, without further ado, let's go into our talk today. I'm going to give you a little reminder from our last TechLabs talk, and basically the format contains both speakers, where they're going to talk shortly about their business and the role of technology in neuroscience for about 20 to 25 minutes each. And after that, we have a short Q&A session for questions from your side. So if you scroll down on the side, you should see our chat field where you could type in your questions one at a time. So feel free to do so. And today, everything should be about neuroscience and how tech solutions could help to make our world easier and better now and in the future. And for this, I'm happy to welcome Surjo from the Charite and Jonathan Naft from Myomo. And I would say, let's start, everybody, let's start first with Surjo. And I'm really excited to get to know a little bit more about neuroscience and your topic and your company. And I do apologize if I'm butchering your names, so please correct me when you start talking.
All right, can everyone hear me?
Mm-hmm.
Great.
Perfect.
There is this slight time delay, but I'm trying to do my best. So my name is Surjo. I work at the Charite since 2018, and I'm here a professor of Clinical Neurotechnology. And well, neurotechnology is any artificial mean to measure or record brain activity. To analyze it, you can analyze it also now in real time, but it's also any tool to modulate brain activity. And if you start the slides now, and just move on to the second slide. Yes, you can see that neurotechnology has been always in the center of the interest of people, especially in the science fiction genre. It has been always a dream of mankind to read out thoughts from brains and translate this into some form of communication with a computer, to read out our memories, or also to influence what is going on in our brain from outside. So this has been in science fiction for a long time, but only a few years ago, if you click further, two figures came to the stage, and they have a lot of money. So you know Elon Musk. He has invested a lot of money into Neuralink, a company that is striving to establish a direct connection between your cortical cells and the computer. And well, there is like some inspiration from also science fiction literature that goes into a neural lace that transforms your thoughts into digital output to a computer that is actually bidirectional. So you can read out and you can also write in. So that's what Elon Musk wants to establish, and I'm going to talk about this in a few minutes. And then there is another actor, Mark Zuckerberg, who wants to do the same. Essentially, he wants to introduce some connection to your smartphone, for example, that does not rely on your fingers. So you are just thinking about writing a text message, and the computer will automatically understand that, reading it out from your brain. So if you click further a few times now, because we have these different means to record brain activity non-invasively, and the most established means non-invasively are magnetoencephalography and electroencephalography, where you record electric or magnetic brain activity from the surface of the skull. And then there are two other measures that you can record. So, for example, you can use quantum sensors. That is a pretty new technology. It's called optically pumped magnetometers. These are sensors that can record brain activity at room temperature. So the conventional MEG uses helium to cool down the sensors to reach the sensitivity to actually record these very, very small magnetic fields. But this is now possible at room temperature at very high spatial resolution, because you can move the sensors really very close to the head. And when you have to cool them with helium, obviously there is some distance. But now we can actually move very, very close to the brain. And another possibility is to shine light through the skull. So you've probably seen that already in the emergency room, in the pulse oxygenization measures in your fingertips, for example. So when you have not sufficient oxygen in your blood, you actually become blue. And the same also applies to your brain. So when you consume a lot of oxygen, the blood in your brain becomes more blue. And that's what you can measure actually from outside of the skull. You can also do this in the MRI, but that's very difficult to move an MRI around if you use a brain-computer interface. But this allows you to really look into the deeper brain areas, like the basal ganglia or the amygdala, so emotion regulation. And of course, you can open the skull and introduce these electrodes that you can see here and record the activity either from the surface of the brain, or you can actually tap into the brain and get in direct contact with neurons. Next slide. So this is a video now that hopefully plays fluent. So if you started, this is the link. Oh, I think you stopped it. Maybe you click again. Okay, this is the robot that implants the threads that are then getting in contact with the cortical tissue. And for me, it's not really moving. I don't know whether you can see it moving. So for me, it's a stent. Now I can see the monkey. Yeah, I can see, yes. It's moving fine. Okay, now you can see a monkey that has been implanted with a device, and the monkey is playing Pong with him or herself. So just by thinking about moving these cursors on the screen, the monkey is moving these cursors in. And here you see the pig. So they implanted this device also in the pig, and they could infer the angles of the joints with this device, and they could also remove the device, and there was no real scar. So they applied now for FDA approval. So it seems that they'll be able to implant this in about 18 to 24 months in a human. And obviously, this will be a real change to the technology that we've been using so far, because only the Utah array was approved by the FDA, which uses 100 microelectrodes that are rigid. And the link of Neuralink uses more than 1,000 connections. So that would really increase the versatility by a lot. So if you click further, so the first clinical brain-computer interface was introduced in the late 90s by Niels Bierbaumer, who enabled a patient who was locked in to select single letters on the screen just by thinking about it. So they used an EEG, and they could record these fluctuations of the EEG to select letters. And in parallel, also brain-computer interfaces were developed that tap into the motor domain. So here you see the demonstrations of the Utah array that was implanted into the motor cortex to control different devices, for example, a robotic arm or stimulators that would stimulate the nerves of the arm. And it's also possible to control 2 prosthetic devices, for example, to eat with cutlery. If you continue now to the next slide. Now, just a few, well, that was last year. A device was implanted in a young man who had a spinal cord injury. You see it here on the left. So he had the injury very high at the cervical level. So he was actually tetraplegic. He could not really move his arms or legs. And they used a fully implantable device that used electrocorticography. So not really invasive in terms of going into the brain tissue, but just being on top of the brain. And if you go to the next slide, this is a demonstration of this young man who was able to control a whole body exoskeleton to, for example, restore gait, so he could move freely. And in another experiment, he could control an exoskeleton in 8 degrees of freedom. So he could reach and tip a target. And this was all decoded from ECOG, electrocorticography. So no real contact to single neurons, but recording the activity of larger number of neurons. So if you continue to the next slide. So this is now a demonstration that you can not only restore movement and tension from your brain, the motor cortex, but you can also implant these devices and drive some electric current through them. And this can be interpreted by the brain as sensory input. So here they implanted 4 UTA arrays, 2 in the motor cortex and 2 in the sensory cortex. And whenever the hand was touching an object, some sensors would create electric patterns that were sent to the array. And with this, the subject would actually feel that the prosthetic device was touching something. And if you now start the video, you can see that with this ability, with this direct stimulation of the cortex on the left side that was with stimulation, on the right side without stimulation, the dexterity that you can achieve with this kind of bidirectional brain-computer interface is really stunning, and you can increase the time that you need to do a certain task by 100%. So the subject needed only 3 seconds, while without sensory feedback through this electric stimulation of his brain, he needed almost 8 seconds. Now, next slide. There are a number of problems now with these implantable devices. Obviously, it involves the risk of infections and bleedings. There is no certification if you want to use this permanently. So usually you have to explant it after 6 months, but you are, like, if you say, well, I don't want to have it explanted, they can't actually force you. So you have it in your brain, but there's no certification actually for this kind of long-term use. And it is also very important to note that these devices cannot be used in daily life independently. So these demonstrations were demonstrations for the media, but the subjects were not really using this in their daily life. Next click. So also, if you want to remove the device, it requires another surgery, which of course is also a big problem. Now, if you have a malfunction, you actually have to open the skull and remove the device. That's the reason, and now next slide. That's the reason why in my work we're focusing really on non-invasive technology. And if you start the video, you can see a number of quadriplegic patients who were unable to grasp different objects of daily life. So, for example, a pen or a book or any other, like a can, for example. We equipped these patients with a brain neural exoskeleton that was attached to their paralyzed hand and fingers. And with this device, they could actually grasp all these different objects of daily life And importantly, they could leave the lab and use the system outside of the laboratory and go to a restaurant, for example, and eat with a fork, for example, that they couldn't do for many years before. So we asked the patients also what they would like to do with the new ability, and one of the patients asked to eat potato chips that he could never eat by himself because his fingers were paralyzed. So we organized the potato chips, and as you can see, the patient was able to feed himself with the potato chips with a device. Okay, if the video is done, just go to the next slide. There is a delay, so I can't actually see what you are seeing. So I hope you can see the video.
The video is running and it's excellent.
Okay. So it's funny. So when I play it from my computer, I can see it, but you can't. And now it's the other way around. So I can't see what you can see. So this is now an example where we implemented the brain neural exoskeleton into a whole arm device. So here you see a young subject controlling this whole arm exoskeleton with his brain and with his eye signals. And there was some artificial intelligence in the system. So the system would recognize objects in front of the wheelchair, for example, a bottle. And it would then be able to just target the bottle, move it, and move it also to the subject's head and mouth, so that the subject could drink from the bottle. So this is the fusion of the brain-computer interface with some artificial intelligence tools like object recognition. And well, this is a shared control paradigm. Now at the end of this video, just go to the next one. It takes a little bit more time now that I don't know what you are seeing, but it's like flying an airplane without seeing where you are. So you see the video right now?
You can continue. We're at BCI triggering. BCI for restoration of gait.
Now go one back, because there's like an important information here in the last slide. I couldn't see.
We're at BCI triggering neuroplasticity.
BCI triggering neuroplasticity, right. So what we could see is when you use the system for a whole month on a daily basis, can everyone see the slide? Okay. So when you do this for a whole month, what happens is that your brain reorganizes. So usually after a severe stroke, both of your hemispheres are active. And when you connect the exoskeleton with your brain, after a month, you can see that the activity is actually shifting to the area that is connected to your hand, which means that, with this kind of paradigm, you can reorganize your brain. And together with this reorganization of the brain, there was some improvement of function. So people could actually move their hands again after sometimes many decades of paralysis. So that is very remarkable. And that tells me that we don't necessarily need to implant electrodes into the brain to restore function, because, well, if you depend on assistance, of course, you need to make this as feasible as possible in everyday life. But if it's about rehabilitation, this non-invasive brain-computer interfaces can trigger plasticity that can actually lead to a situation where you don't need the exoskeleton anymore after a while. So if you continue now to the next slide, and we'll just speed up a little bit now because we have lost a few minutes. Now let's go to the next one. This video shows you that this was also shown in lower limb SCI, spinal cord injuries. So there's also rehabilitation happening here. But if you go to the next slide, this is a rat that should not be able to move, actually. But you can see it moving. Can you see it moving? Because I don't see anything. Can you see it moving?
Yeah, now we're at adaptive neurostimulation.
Yes. So Well, the same principle was implemented in spinal cord injuries with a stimulator that was implanted below the lesion. And they didn't use cortical signals from the brain, but they used signals from the chest. So when you would lean forward, they would use this information to start the stimulation, to initiate gait movements. And with this, the people could actually start walking. So I don't see whether you can see it. Do you see a patient walk now? I don't see anything. So I
Yes,
can't
now
see
we're
actually
looking
the
at
video.
someone adaptive neurostimulation, and someone is
Okay, so he's
using
moving
their
the leg.
leg
So
to kick.
right.
Yeah.
Yes. Yes. So after a few months, the patient who was completely paralyzed before couldn't move his leg is actually moving his leg. And a few more months later, the patient could even walk without sticks. So this is a very good example of the plasticity that you can induce with this kind of technology if you do it at the right time in the right manner. And the amount of restoration of movement that you can actually introduce with this kind of neurotechnology. Now, there are a number of companies that are going into this direction and develop exoskeletons for assistance in daily life. So you see the handy rehab. So this is very new. So there are not so many companies that are working in this field, and I'm very glad that we have John now as the follow speaker, who will show you where we are right now. But in the end, if we can read out from the brain and we don't have devices to actually help you in everyday life, the whole brain-computer interface is useless. So what we need is the actuators, and it's so nice to have this collaboration now with John to get something that is really meaningful to the patients. But if you go now to the next slide, I wanted to discuss what's actually in the next step. So this is the next generation BCI. So right now we are using brain activity to, for example, use an exoskeleton to grasp a cup, and you receive sensory feedback that also changes brain activity, and this closed loop can be used to introduce synaptic and like structural and functional plasticity. In the future, what we also want to do is we want to extend that. If you go to the next click, in the future, we want to extend this principle. Now click further to the next generation BCI, and there is also brain activity translated into sensory feedback, but we'll use brain activity related to other brain functions like working memory, motion regulation, or also sensory motor integration. But to do this, we need to understand what are the substrates, the brain activity that is related to these brain functions. And to do this, if you go to the next slide, yes, we will use brain stimulation. And the problem with the brain stimulation, that was very fast now. The problem with the brain stimulation is that if you introduce brain stimulation, you cannot read out the signals from the brain because the stimulation signal is so strong. But we have, if you click now, we have now introduced methods that allow us actually to record brain activity while we stimulate the brain directly or stimulate the body. And this allows us to really identify the neural substrates of different brain functions like emotion regulation and cognitive control. If you continue. So we have also implemented this for alternating current stimulation to target different frequencies in the brain. If you continue. This is all working now, also with alternating current. If you continue further. We have also developed a new stimulation device that does this fully non-invasively with magnetic fields that interfere at a certain point in your brain. And with this, we can also target deeper brain areas. So this is very exciting work because usually there's volume conduction. It's very hard to predict where the electric current, if you apply it to the brain, actually hits your brain tissue. But with this magnetic method, you can be very precise to the millimeter precise, and you can also target deeper brain areas. So this is a method that will hopefully be also used in patient treatment. If you continue now, I'll try to come to an end now. So summarize the first part. So I've shown that brain-computer interfaces are very powerful tools to restore quality of life in paralysis. And I've shown that if you use these devices on a regular basis, on a daily basis, you can trigger neuroplasticity that relates to neurological recovery. And I've also mentioned that we are now pushing the frontier to also mental and cognitive functions by combining these BCIs with brain stimulation. And we're also developing new brain stimulation techniques that are more focal and more precise. Now, if you go to the next slide, so the three big challenges in brain-computer interfacing and all this neurotechnology is these three input-output constraints. So right now we can only extract 1 to 4 bits from the brain, but there are trillions of bits in the brain encoded. And of course, there's a long way to go to actually tap into this kind of ocean of information. The other problem that we are trying to address also with the combination with brain stimulation is the brain-behavior relationship. So we need to understand how the brain activity really links to behavior and to your thoughts. So that is very difficult because it's very individual. But my hope is that with these bidirectional brain-computer interfaces, we'll be able to take the next steps towards that goal. And the third dimension is we have to develop effective tools to specifically modulate brain activity. So really on a cellular basis, and this, if you click, has not been achieved yet at all. So we are putting these large electrodes on the surface of the head, and it's very clumsy. So if you go to the next slide, in the future, what we can envision is if we increase using machine learning the readout from the brain to, let's say, a little bit more, we will still only see the brain-computer interfaces in maybe gaming and lifestyle products, but we will not see it in everyday life. If you click to the next, if we increase further, if we increase the bit rate to 60 to 80 bit per second, this would be equivalent to fluent mind reading. So then this would be really game changer for like everyone. You could then use it for your smartphone, and it would really provide a lot of advantages for you. Now, if you continue further, if we achieve like a billion bits per second, we could maybe even reach a full fusion with a computer. But this is so far out of reach now that it's really science fiction. Now, next slide. If we implement all these technologies, it is very important to see that there are a lot of neuroethical questions that need to be considered, like data security and also responsibility, accountability. And these issues, these neuroethical issues, have to be addressed, and rather before we actually have these tools at our hand. So if I summarize now, if you go to the last slide, neurotechnology is now rapidly advancing and is now already about to enter everyday life environments, currently in the medical field, but maybe in the future also in other like non-medical fields. And there are 3 possible future scenarios. I mentioned status quo plus, so just gaming and medicine, but then mind reading or full fusion. And introducing neurotechnology to the masses, of course, raises many neuroethical questions that we need to address now. And well, it is critical to inform the users about the possibilities of neurotechnology, and that's why I'm giving this talk here. And I'm very eager to discuss this all with you now, also after John showing his slides. And with this, I would like to thank you very much for your attention. It's a great pleasure to be here.
Thank you so much, Surjo. It was really, really inspiring, the work that you've done. Some of that work actually inspired me. Well, the precursors of that work inspired me to get into neuroscience in the first place. So I'm really, it was really great to see all of the advances. Now we're going to go over and talk to Jonathan, and he's going to give us the flip side, I guess, the in practice, neuroscience and technology mashup in practice. I'll send it over to you now, John.
Thank you. Thank you very much. I'll share my screen. First off, thanks to Professor for such a nice segue into my talk. I think you're exactly right. If we don't develop appropriate things for the body once we receive the signal, We just need to stay ahead of the work of what's coming out of the brain signals so that we can incorporate these devices on people's bodies easily. And it's also a pleasure to work with you and your team at Charite. As well, thank you very much to the TechLabs group for bringing this together. I think these are important conversations to have, and collaboration is really a necessity for all of us to continue to advance this. So my presentation here is focused on what we can build to put on people's bodies so that when we take these signals that come from the body, we can put them to good use, not just in the laboratory, but in the homes of people who need them and out in the community. And my background is in engineering, and I'm also a certified prosthetist and orthotist. So my expertise is really in designing and fitting devices that go on the body to help those function a little bit better in their life. Our company is called Myomo, and we are headquartered in Boston in the United States. I'm speaking to you today from the United States. I also would like to say I wish everyone well as we emerge from COVID. I hope that you and your families are well, and that we finally can put some of this behind us and can travel again and collaborate. I miss my visits over to Germany, in particular Berlin as well. So my own motion is how the company got started, because when one of the first braces was put on a patient's arm and she moved her arm, she said, wow, this is like my own motion. So let me get this presentation going. In the United States alone, we have close to 800,000 people who have a stroke every year. And when you start adding those numbers up across the world, it's a very large number of people who have trouble moving their limbs, whether it's from stroke or spinal cord, brachial plexus, or other neurological diseases or injuries. It's a very large number of people. This creates a very significant problem beyond the patient themselves. People need to provide help for people's loss of function in their home. So if someone wants to be at home, they may have to have others come in and help them. And that's very taxing for dependence on caregivers. It's very difficult. It's also very expensive. So how did we get started with our device? There was a student at the Massachusetts Institute of Technology here in the United States that essentially got the question started that said, if you look at my picture on the left here, if you are an amputee and you are missing your arm, you get a powered prosthetic arm. And that powered prosthetic arm can open and close fingers, flex and extend the elbow. But if you still have your arm and you can't move it, there is not as many options available. So at Myomo, with a real team environment, everyone worked hard to produce what you see on the screen here, which is our current device that's in the field. I believe that we have a little over 1,400 of these units out. These devices go home with people, and in many countries, they are now beginning to have coverage, of course, from insurance companies, which is a real necessity because if we design these devices in the lab, we really need a means to get them on people in their homes. Some highlights on this device. It's considering its size, it's very lightweight. It's approximately in the US around 3 pounds. It has a rechargeable battery, which depending on the user's use can last anywhere from 2 days up to 2 weeks. No patient has ever worn out a battery in a day, and they are rechargeable. They insert right into the device so that if someone does run out of their battery, they just flip a new one in. There are 4 sensors that sit on top of the patient's skin in their arm to detect EMG, electromyography, which is the patient's intention to really move that arm is what we're really reading. So we have one on the bicep and tricep, and then both on the volar and dorsal surfaces of the forearm. There's a motor that will move the elbow to flex and extend, and there's a motor at the hand which will move the fingers to open and close. Currently, most of our patients are adults, and we've been starting to expand into adolescents. By far, the biggest number of people we see are stroke patients. Coming up a close second are brachial plexus individuals, and then we're now doing research with patients with spinal cord and some other difficult diagnoses. We're also very excited to be working with children. I've had the pleasure of fitting several children with some of our prototype devices, and those are just outstanding and fun. Most of those children were diagnosed with such things as cerebral palsy, which can present with the same spasticity we see on stroke patients. So as we just learned in the previous talk, we can get waves from different places in the body. Someday I look forward to being able to take those waves directly from the brain into our device in real time. For now, what we take them is from the surface of the skin, which is very, very safe. It's long proven since the 1960s. So this picture shows you an example of the surface electrode that we take from the skin. But as was also pointed out, taking signals from the skin is subject to other complexities and difficulties. If we can truly take the signals either directly from the muscles or directly from the brain, we can get a purer signal. But for now, this has been working very well. And this is also the same as people who wear a prosthetic if they have an amputation of the arm. The way this works is one's brain generates the intention to move. That intention then travels through the brain, through the spinal cord, and down into the muscles of the patient's body. Once that signal reaches the muscle, the sensor can detect the electrical potential across the heads of the sensor and measure that. And if we can measure that, then our computer on board can process those signals and make commands to move the motors. The resulting motor movement can be used by the patients to open and close their hand and flex and extend their elbow when they otherwise can't do it at all. So this is a video showing one of our engineers. You will notice in this case, the electrodes are wrapped underneath the bands on the bicep, on the upper arm and tricep, and on the forearm. Now what you see on the screen is the readout of the electromyography. The blue line is the bicep, the red line is the tricep. So this is kind of a rectified and very pretty graph. And you can see that when the EMG goes up, the brace will go up, and when it goes down, the brace can go down as well. Some of you may have noticed a slight lag in the video. What we have also found is that speed of the time in real time when an EMG is sensed by the motors on a patient with spasticity, it can be very important to actually slow the device down a little bit in terms of what we call response time. This response time on a spastic patient allows for the device to move much more smooth and fluid. So here's a picture of one of our patients with and without the device at his home, picking up leaves, just general activities. Some of the simple tasks can be most exciting to do, with our device, such as, holding a cucumber to prepare a meal to cook. This particular patient, you can see from the smile on his face, he loves to eat yogurt at the end of the day, and it's very satisfying for him to be able to do it himself. I should note that each device is made one at a time from a mold of the patient's arm and measurements, and this can also be done with 3D scanning. It can be done with measurements, 3D printing, lots of ways to make the device. Here's a collage of an individual. This patient is a stroke patient. So what's wonderful about this example is he has good shoulder range of motion, but he is unable to flex and extend his elbow and unable to open and close his hand. So it's really an ideal situation for our device. So he was fitted here in the United States, and he gets to take the device home. So you'll see how nice his finger movement is, and the tasks that he can do. Eventually we will, progress to the shoulder. We will have all 5 fingers and doing all kinds of neat things. So I went to this patient's home to watch him do some of these tasks. He was excited to be able to do things such as moving his furniture around. Now you should note that that chair is actually very light. It's hollow plastic. The device is not designed to lift heavy objects, only a few pounds. It's really designed just to support your arm for basic tasks. But this is an example of how the support of your arm, even on small tasks, such as just writing and holding paper, are very important. So I feel like we're making good progress on this. I'm going to show you next a clinical application. So this is a patient who's had a brachial plexus injury. He's had multiple surgeries to try to reinnervate his arm. You can see he can barely just move his fingers, but with no strength. This patient also has good shoulder movement, but he has no ability to bend his elbow. What's important too is that we understand the frustration these patients have. So this is a patient who wants to return to work. He wants to return to being independent, but he's very frustrated because those are things that are difficult when you can only use one arm. So we were fortunate that he, like many others, had good insurance coverage. So he was prescribed the device from his physician in the United States. And you can see here in the video, this is him training with the device. Flex and extend his elbow, and then you'll see him opening and closing his hand. Here's a close-up of his hand opening and closing. Now remember, what's most important here is this is not a machine that's doing this automatically. He moves this with the thoughts that start with his brain and travel through his spinal cord into his arm, to his muscles. So the machine will only work when he commands it to do so volitionally. Now, the nice thing is you can regain function very quickly. So things that were otherwise hard to do with that arm. And if you look closely, it's my favorite part. You'll see him start to smile because he's very happy that he can do things. Here's another example. We were going to do some outcome measure testing. So he intuitively now goes back to using that arm. I asked him to get his belongings, and without even putting much thought into it, he automatically reached with his right arm because he's right-handed. You can see we also use this adaptation we call the pinchers. These are small paddles on the end of the device. This patient wanted to try doing some things that he was working on before his accident, such as a hammer and a nail. Now, to be clear, we don't recommend that patients put hammers too close to our device. We do use caution. Now, here's the amazing part. Patients with their arms, if they have no device, they don't use their arm. And when you don't use your arm gets weaker. But now if you use your arm every day, especially for supports and function, the more you use your arm, then you're just allowing for greater neuroplasticity, you allow for greater strength, and you allow for greater happiness. Now we don't declare that patients will graduate out of this device, but we do see patients getting stronger. And the primary indication of our device is used to support your arm. So that, I think, brings me to the end of the discussion. So I will turn it back over. I always welcome collaboration and comments. Feel free to contact me and email me at Myomo. And I'm looking forward to seeing this continue to grow, especially with the exciting things that we just saw with brain control interface. If we get a good signal, our engineering team, myself and the other clinicians, we can interpret the signal to make the motors work. So thank you very much. It's really fun to be here with you today, and I look forward to any questions.
Thank you so much, John. That was actually really informative as well. I think I'm having a really great time today. It gets me back into something, like I said before, it's really near and dear to my heart, which is neuroscience. I have a question to kick off the Q&A, and it's, I guess, directed at both of you. I can ask you first, Surjo. I was looking at the results of the people that you were using in your patients, and I was wondering, is there any age limitations for this? Are younger people more able to use, or do you see better results in younger people rather than older people, or do you have enough? Have you done enough studies to say anything about that?
Well, this is a very good question, and what we can say is that well, there are a few factors that increase the probability that you are doing really well from the first session on. And that is that you are playing or that you played, for example, a piano or some musical instrument. And obviously, the lesion location is very important if you're talking about brain-computer interfaces in patient populations. So in healthy volunteers, obviously, if you play an instrument or so, this really helps you. Or if you do meditation, for example, it has clearly an effect on how well you can learn to control the BCI. But everyone can learn it. It's all operant conditioning of your brain activity, and it's all about training. So some people need a little bit longer, like 2 or 3 days to control it, and others, they can just do it from the first moment. And I would say, well, the older you are, of course, the more difficult it becomes to learn new tasks. With the BCI, it is a little bit similar. So if you train stroke patients, you have to acknowledge that it is sometimes quite exhausting for them, and you have to take more sessions. So usually it takes sometimes twice as much time. So it takes a week more or less to control a BCI quite well. But for example, in SCI, these are very young patients. Most of the patients could do it from the first session on, and they really reached good performance. So it's a little bit hard to predict.
And I think it's related to your slides too, John, because I saw you are dealing with many stroke patients. So stroke patients typically, I would imagine, are older people. So is that correct? Or do you see any differences in the aging?
Yeah, I think it's a great point. Most of the patients here that we see are adults, and again, most of them are stroke, as you've indicated. But it's a perfect segue into a question I just saw on the Slido app. Somebody was asking, what is the next great thing that we hope to produce out of Myomo? As a lot of people have seen some of our content, we've been fitting children. So I think the youngest I fit was 5 years old. So I fit a young person 5 years old, fit several 6-year-old, 8-year-olds, and they're very fun, very eager to learn. You still have to learn to control the device, and I think that's the biggest thing for us that you're going to see next is better ways to control the device, smoother algorithms, smaller, lighter brace. We've been experimenting with training using video games, especially with children. So you can put a video game on the screen. But what we found was our adults are working very well with the video games, which is our current device on the market. So training using these games is really helpful. So I guess in summary, to answer the question, I think, for learning to control our device, we're fortunate that the adults seem to learn it fast. I think the children will learn it slightly faster.
I think there's a combined question next, and it's about I guess, when do you think it'll be possible to reconnect nerves, for example, at the spine, so people can move without having these devices? Or do you think that'll be possible at some point in the future? That was a popular question on our Slido.
Yeah, I think I'll defer that one to the professor. My expertise is actually the opposite. So we work on, we work once we get a signal from the body, we build devices that go on the body. I do think that that's
This is
in
almost
our future. Yeah, it's not something that I'm actively working on now, but I do hope to see that one day for all the people who need it. But what my focus mostly is on is patients today or literally tomorrow. We're fortunate to have a device which we have on the market, which patients are actively using, and at the same time, we partner with great organizations like Charite, so that we're always looking ahead to the future.
I'm thinking that almost sounds like a prosthetic nervous system, which is interesting. It's like bringing it into the body, but yeah. Other question I think a lot of these raise are the ethical questions. So especially I think when you got into speaking about using or getting the signals to, I guess, influence emotions or cognition and things like that. What do you think are the greatest, ethical challenges that you see first on the medical side, and then for you, John, on the technical side, do you see people using these to enhance what we say normal physical performance?
Professor, are you going first on that one?
So I start. Okay. So well, the neuroethical dimensions are manifold. So right now, what we can see is that obviously what is interesting is to get this information, get this data, and infer different user states. For example, that is the start. And then the question is, okay, if you provide this data to a company, it's not really under your control anymore so much. We've seen this in your interaction with, for example, internet browsers and interactions with other software. So I think people need to know that if we are providing all this information, also our biosignals, that more information, of course, can be inferred, and that's only the start. And because the next step would be that I haven't been showing this because the time was so short. There is some form of technology called neuroadaptive neurotechnology, neuroadaptive technology. So here we are using brain responses relative to sensory stimuli to infer desired goals, desired outcomes of users. So this, of course, is all unconscious or not really conscious. And this taps into an area where you need a clear consent that this kind of information can be taken out and used for different purposes. So in my field, we are only exclusively working on medical applications, and there is like an ethical imperative to use our knowledge to improve quality of life of these people. But it also shows how far we already can go with this kind of technology, also using this in everyday life. And this is only a matter of time. It's not the question whether this will happen, but it's only the question when it will happen. And I think we need to think a little bit forward and already anticipate how this data could be used and make sure that it's not abused.
Yeah, exactly. I was thinking just that as you were describing it. There's a movie, Minority Report, and a lot of the things sound like straight out of that. So that's the kind of the fear, right, of many people. So I think you're right, getting ahead of it and planning for it, I guess, pre-policy making or whatever, to get the technology caught up or before people run amok with it would be a good idea. And on your side, John, were you going to add? anything to this?
Yeah, I do. I think it's a really fascinating and fun discussion. So machines, they work with control systems, and where the control system comes from is what drives the device, and that's what is the intent. That's what drives what's the intended use of the device. So, for example, if I'm in my home and I want to play some music or turn a light switch on and off, I can either just use my voice waves from my mouth, and I could command Google or Alexa to turn on a light switch or play my favorite song. And what we've chosen to do at Myomo is focus on control systems specifically for the human body, for the betterment of the human body, and for people who need those technologies. Every day we get patients that are sent to our facilities, and these are patients who really want and need a device to help them with their daily life. And they need these devices as soon as possible. So, things that we have to look out for are, unfortunately, in the world, it's just cybersecurity, things like hacking, intended use. So, what would these devices be built for in the future? I think is going to be very interesting. But our focus right now is on health.
Yes. I noticed something in the videos. You had people, you mentioned it twice, John, about having a good shoulder strength. Is that something that's necessary for good use of the device, or can anyone use it?
That's a great question. So I'll try to show you an example here on the screen. So if I have a bottle, let's say it's up here, I'll change hands. So let's say the bottle's up here and I want to grab it with my right arm. So with this device, our MyoPro, you can bend your elbow and now you can open and close your hand. But if you want to grab the bottle, you need some active range of motion at your shoulder to be able to reach for it. So your shoulder will control your function. But we're also seeing value for people who don't have shoulder movement. So, for example, let's say one is just sitting in a chair and they want to open the bottle. As long as you can get the bottle in your hand, then you could use perhaps your sound side to open the bottle. Or you don't necessarily need your shoulder if you want to look somebody in the eye on your cell phone, or if you want to dial in a number. So what we have found is, of course, the more active shoulder range of motion you have, the bigger the area of space you can work in. The less shoulder range that you have, then you just need to work closer to your body. So there's value for both, and it's something that we're continuing to work on and grow over time.
I think one thing that was interesting in both the videos was seeing the smiles on the faces of the patients once they got their mobility back. So I think that the work that both of you are doing goes such a long way for that's the social emotional health of people, not including, of course, their physical, mobility, but also being able to rejoin society, whether you're locked in or whether you are you've lost control, like the gentleman using his opening his yogurt and being so happy that he could do something so simple as eat yogurt. What was amazing, just as amazing as seeing the boy that was a quadriplegic or paraplegic walk again. So I think both of these, I guess it's one technology kind of with two manifestations or different manifestations of the same area, can do a lot or go a long way to helping people feel reconnected and useful in society, even though they are useful, but having that, kind of affirmation that, they can they can motivate themselves to do what they want to do when they want to do it and not rely so much on others to help them is a really great thing.
Yeah, it's actually, I'm glad you brought that up because it's one of my favorite parts of my job. Most of these patients who have paralysis of part of their body, they're told, you may never use your arm again. or if you are going to use your arm, the progress will be very, very slow over years and years and years. And then you watch them put the device on, and then they, can open and close their hand within maybe 10 minutes of practice, just basic operation. Same with flex and extend, and then they get to take it home. So that's probably for me, one of the more exciting and rewarding parts of the job, because unfortunately, they're told the opposite of many other. These patients are told the opposite of many other medical interventions. So, for example, if an amputee has to have an amputation, they're told, well, you're going to get a prosthetic and you'll start walking, or you'll get a prosthetic arm and you can start using it. But when your body has paralysis, you're essentially told, we don't know how long your paralysis will be. It may never come back. So, that's probably the most exciting part of where we're going. And then, the challenge is to make it better. So, for now, we open and close the hand in a 3-jaw chuck. So we're making patients very happy because they can do basic things like, hold their yogurt. But, ideally, someday I'd like to see them playing piano with both hands when they never played piano.
I wasn't going to say anything.
So
I didn't want to push you too far, but yeah, that's where the magic of marrying the two technologies together could happen, like getting those signals directly from the brain and into the device can really help that happen.
Now, what I also wanted to raise now, maybe we're already a little bit over time, but what is so important, when I started in neurology many years ago, it was like John said, after rehabilitation efforts, if they were not really working out well, the physicians would say, well, that's it. So this is how it is. And if you don't train, you will actually lose more of function. But for example, if you don't have finger functions, you'll never get it back. That was the status maybe 20 years ago. And this has really changed, and we can show how plastic the brain is, and that we can actually restore function in some cases, not in all cases. And that also has like a lot of ethical implications, because, well, the problem is we don't have biomarkers. We don't know how much we can restore in a single patient. We don't want to promise, of course. That is also not very, very good if people have too high expectations. So that's the reason why I like this combination of assistance and rehabilitation, that we use assistive devices for a certain time to see how well we can trigger neuroplasticity. And that's why it makes so much sense to collaborate with John to say, okay, we have this assistive device and we'll see how much the nervous system can actually recover. And if it doesn't really recover, we still have the assistive function. And that's where, I think we can be very honest to the patient and say, okay, look, this is what you can get with a device, and this is what you will get. And maybe you can get even a little bit more, and you get, as he showed, more strength in your arm and maybe some more function with the fingers. And maybe that will be sufficient to be more versatile with control of the device using EMG later on, which you don't get if in early stages because of spasticity and so on. But we've shown that in some cases, not in all cases, but in some cases, you can restore like this kind of muscle control and have a more versatile command of the device. So that is what I really would like to see in the future in our hospitals, that we are not overselling, but telling them, okay, this is what you will get. And if you train hard, you'll see that your arm gets better and better. And of course, some will improve in terms of like rehabilitation, and some will just stay at this assistive level, which still is better than nothing. So that's what also motivates me.
Thank you both so much. It's been really informative and exciting. And I think everyone working at TechLabs, working with TechLabs, has really great ideas, or hopefully has some great ideas about how they can incorporate this into the work that they're doing, especially through more AI and just data. It's really, really exciting. Do you have any last words? I'll let you go, John, first, and then we can go with Surjo.
Sure. I think, again, I just would like to thank you for hosting this platform and giving us all a chance to collaborate. And the my last words are, some of this isn't the future. A lot of it's already happening now. And I would just encourage everyone to continue sharing dialogue. Let's keep pushing the envelope forward so that, there's that metaphor that, the future always starts today. So thanks very much for having me.
Thank you. And Surjo?
Yes, and did
I get it right now, Surjo?
Yes, what John was saying. So it was a great pleasure to talk here today. I must apologize for the technical difficulties. So no, at Charite, we are on top of technology, but the internet connection is really bad. So I'm sorry for that. If you're interested to visit us here in Berlin and have a direct contact to this kind of technology, you're always cordially invited to just come here and have a look. So we're also doing a lot of neuromodulation, as I mentioned in my talk. So this is the future. Obviously, it will take a few more years, but if I see what we've already achieved in the last years, it's absolutely amazing. And what I really want to achieve in the next 10 years is that we are actually getting at the end of the translational pipeline and really see this in broad application in the hospitals, improving quality of life. So that's all. It was a great pleasure to be here, and it's always good to see John.
Thank you both, and thank you for making this talk series wonderful. Hope to have you back again soon. Bye. Bye, everyone.